All right. Welcome back. So we have an not even shortlist. This is actual IMO5 apparently. Um, Asking, can you put 1987 points in R squared such that um, every pair of points has a rational distance, and every 3 points um, determine a non-degenerate triangle with rational area. How do you do this? Hang on. Um, Wait. Okay, come on. Like, this has got to be. So okay, here's the thing. By the shoelace formula, or actually not shoelace. What do you call it? No, it is shoelace. Um, so lemma. Uh, Given a bunch of any triangle with vertices which are lattice points has rational area. Because I was gonna say like guaranteeing rational area seemed really annoying, and up until this is true. So as long as I can put the points on the lattice such that so yeah, rational area is easy to guarantee as even heck, not even like lattice points. Just if the points have rational x y coordinates, that's good enough. Doesn't matter because we can scale. But yeah. So all I need to do is make sure that there are no integer. I need to make sure that none of the lengths are integers, and that should actually be pretty easy because relatively speaking, Pythagorean triples are pretty rare, right? Right? Is that true? Uh. Yeah, Pythagorean triples are um like if I pick two random integers like x and y, I almost never expect x squared plus y squared to actually be an integer. So I should just be able to run it over, right? Yeah, just it feels like I should just be able to run it over. Okay, so lemma claim there shouldn't be there's not enough to stop us, so we're just gonna run with it. Claim given a finite set S. Of lattice points, we can add one lattice point without. We can add one lattice point p, such that p is irrational distance from every. Um, from every point in S. And what's the best way to do this? Can I just take what's the cleanest way to do this? So suppose S lies inside 0m times 0m without loss of generality. So put it in a big box, and I think the idea is I'm going to just take a point that's like close to a Pythagorean triple, and let's just nudge it a tiny bit. It should be okay. Maybe? Let's find out. I'm gonna use 1m actually. 1m, 1m. And I claim that p equals 3000m, 4000m is okay. Because the distance from I might eat my words in just a moment. However, I feel like to a point UV is 3000m minus u squared plus 4000m minus v squared, which is 25 million m. Oh shit, the constants might actually be not that small. I mean, the point is it's 5000 m squared plus like a small perturbation, which is like, ah shit, it might be too big. 6. 6, 37, 14,000. 6,000 U plus 8,000 V times M. Integer area. Yeah, I think I would probably write integer area too if I was writing the problem. I don't think it really matters. Okay, well, where was I? Okay, I think my construction didn't actually work. Crap. Yeah, I was hoping it would be like the distance to the nearest perfect square is like 10,000 m-ish. So this will be bigger than... This can be up to... 14,000? I think I should pick something bigger than M here. If I just make this big enough, is it still okay? I feel like, actually, I get to control how big it is. The errors are on the order of... Ah, god damn it. Okay, we're gonna call this n, alright? And we're gonna say let m equals 1,000, 10,000 n to the 1,000 or something. I don't know. 3m, 4m. Well, you know, just drop this act. I don't need to make it like 1,000 n. I can make it as big as I want. So this will be this will never be a square as long as 6u plus 8v God damn it. I think this might not be good enough. So this is up until... Six U plus 8V. Are you trying to bound the distance between two integers? Yeah, I think it's too big. Like what I was hoping was I could say this is like bigger than 5m minus 5 capital M minus 1 all squared, but that's not true. Yeah, that's just not true. It does feel like the farther away I am from the points in S, the easier of a time I should have. So what I could try to say is like, Alright, we're gonna take a short ad break while I think quietly to myself for a small number of minutes. Where's the ad break button? Alright. Accidentally. Yes, definitely an accident. Alright, welcome back. Alright, okay, so here, I think we'll do it. Let M be big. So consider large M. I claim that 3M, 4M is okay if M is sufficiently large. I think that's the claim. So Actually, I don't like the letter M. Can I use the capital A or something? Okay, we're gonna use lowercase n for this and capital C for this. C, 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 C. So for this to be a square, it must be inside the set. Alright, so 6a plus, okay, minus 7 n squared. 5c minus 7n plus 1 squared. So this goes all the way up until like, so let's see, that error term is about 2n squared. So if I just put 2 in here, it's that's a good enough bound, right? So the square distance, we'll call this d. I feel like I'm confusing myself. Something feels really off to me. No, this should be okay, right? So this is this is at most minus 14 nc. This is at the upper side is at most like 2n squared. So there's only 9n different squares in this set, right? It's like, okay, I don't know exactly which values of d it is. Does this work? Am I being stupid? Somehow this feels. Okay, I'm gonna change C to R actually. I don't like C. I thought I just checked that it's not good enough for d to just be like a random large number. But this seems to be a proof that if d is greater than 5r plus 2n all squared. Hang on, I'm so confused. Oh, okay. I'm confusing capital R and D. Okay. So, given any set of lattice points, isn't it really easy? It feels like it should be really easy, but I'm like crashing into a wall and dying. I mean, that's what I'm trying to do. I agree. It seems like it should be easy. Like in the sense that, if I haven't figured out how to do it in 1 hour, I will be very disappointed. But I wrote this thing down, and I want to know if it works, even though, honestly, probably I should. It's easier if I just, like, do a different general strategy, because this one seems to be really annoying. But this should work. And here, okay, here's why it works. Okay, I'm gonna, yeah. There's gotta be an easier way to do it, I agree. But this is gonna work, so I'm just gonna make it work because I don't want to start over because I'm lazy. Say a lattice point is cute if its distance from the origin is irrational. Wait, shit. Wait, 3R, 4R is by definition not cute. Oh, fuck. Hang on. So in other words, if R is large enough, then D is not a square unless D is actually identically the square of a polynomial in R. For that to be the case, we would need D equals like 5R minus square root. Wow, wait, I'm so confused why this is putting up such a fight, is the thing. Which would only happen if square root u squared plus v squared equals 6u plus 8v. Does that ever happen? Are there integers such that 10 root u squared plus v squared equals 6u plus 8v? Also, why am I doing it this way? There's gotta be a better way to do this, right? Like, come on. But basically what's happening, if you have a quadratic polynomial with perfect square leading coefficient, unless the polynomial is literally the square of a linear thing, then it will not be a square for large enough inputs, is the way the theorem works. Because you can trap it between some squares. So I need to make sure that this thing doesn't have too many integer solutions, which is true. It has to be true. Alright, I'm just gonna plug this into Wolfram Alpha and see what it tells me. Are you fucking kidding me? Hang on. I'm learning so much from this problem. Okay. So I've been trying. Okay, I'm sorry. I'm a stupid head. I just made a. If you actually imagine this construction, all right, here's what's going to happen. All the points are collinear. If the points are collinear, this construction is really not going to fucking work. So, yeah, I was looking at this like, why is this putting up such a fight? And the reason is that, well, it doesn't work because the points are literally on the line y over x equals 4 over 3. So of course the property won't work. Okay, new plan. Let alpha and beta be integers such that x over y does not equal. So we're gonna remove that obstruction. Okay, well actually let a squared plus b squared equals c squared be a Pythagorean triple with the additional property. This is so stupid. What? That a over b does not equal x over y for any x, y, and s. And this is possible because there are infinitely many Pythagorean triples. Okay, so we're going to do the whole thing that I just did, except instead of 3 and 4, I'm just going to write a and b, and it should just work now. 3b, so c, au, 2au plus bv plus u squared plus v squared. And then this whole thing works, except instead of 7, I have to write a plus b here, a plus b, a plus... No, this one can still be 2. Okay, so for that to happen, I would need this, which would only happen if c u squared plus v squared equals 2au plus 2bv. And what I just learned is that this thing actually does factor quite nicely. It's 2au plus 2b. Thank you, Wolfram Alpha, for your wisdom. God damn it, I hate everything. Hang on. See. 2a, wait, I'm missing a factor of 2. Which factorized am I missing? Oh, there's no AU here. I'm stupid. Wow, this is so... BU minus AV squared. Which doesn't happen because we chose AB not equal to X over... So hence for each point, oh my god, this is going so far off the page. So hence for each UV and S, there exists a constant C UV for which R greater than C UV is good enough. So take the max of these finitely many constants to finish. So see, I told you it'd work. I did not expect it. Okay, it actually did work. You just needed to fix it. I just wanted to use 3, 4 because I assumed it would be totally fine. But you actually, for this construction to work, you need to not pick a ratio that you already have. All right, we did it, fam. I guess I'll do the write-up. I'm excited to see what one-line solution is on the ALPS, because there's I don't think this is the intended solution. In the sense, like chat was saying, there's so much freedom that there are probably a lot of constructions, and I would be astonished if this was the shortest one anyone's found. Okay, so... Okay, so here's what the write-up looks like so far. We can hide the Mythargia thing because we're done with that game. Okay, so given a finite set, I want to say primitive. if R is large enough, then you know. Okay. Cute problem. I feel like I hesitate to call this geometry because it's not really a geometric. We're gonna call this, you know what, we're gonna call this number theory, alright? We'll call this a number theory problem. That construct free wasteful design. Okay, and then where's the ops thread? Shit. One, please. Where's the... No, this is the wrong one. Shit, come on. Where's the thread? Where did I put it? Okay, we're gonna dig it out. Okay, I think this is a different thread than whatever I was given originally. But that's fine. Oops, wow, I'm really clumsy today. I'm just doing all the wrong things. And of course, alright, black blue car literally beat me too. Alright, nice snipe. Yeah. Just take points on the parabola. Wow, okay, parabola works. Very nice, very nice. Yeah. That's about what I expected. Cool. Cool.